Hello community, so great that you are back. Yes, absolutely a fascinating title for today's talk. And of course you are on my channel Discover AI, where we talk about the latest AI research paper. Now what does have Georgia Institute of Tech, MIT and Nvidia in common if they publish here their latest AI research? You guessed it, it is about LLM reasoning. And if you have seen here my last video where we talk about real-time reasoning, so extreme fast reasoning for integration in robotics or human-computer interfaces or whatever, you know that this is not a study depth introduction, one of two papers of today. Efficiency of LLM reasoning, Georgia Tech, MIT, Nvidia. Let's have a look. Just imagine you give the same task to two brilliant mathematicians. One solves here a complex Turing by filling up here in the classroom, I think about 8-10 blackboards with some beautiful calculation, takes him about 2 hours. And the other mathematician has another form of intelligence. After 2-3 minutes he says, I understand now. I can come up with a concise logic and present to you the solution. So you see, both arrive at the same conclusion, but the second one shows a much deeper, much more efficient form of intelligence. And this is exactly what we are talking about today in AI. We want this in AI. What we do not want is a Nemotron 7B LLM that has a latency of 3,300 milliseconds and a token length for the reasoning process of 9,000 tokens to arrive at the conclusion, at the result. If we have, on the other hand, a little Sky T1 7B, so the same size does not matter anymore, in some cases here, and this has a performance here to be 11 times faster and 20 times fewer tokens for the same result. And Nvidia says, okay, this is what we are interested in. For those models, we want to approximate here or to improve here our training procedures. Latency, cost, energy. Let's see. Now, if you say, what the hell is Sky T1? You just go to my channel, you put in the search Sky T1, and you see 9 months ago, I did a beautiful video where I explained in detail how Sky T1 by UC Berkeley was created, what were the reasoning traces, what was the base model, what was the teacher-student learning process in detail, and you know everything that you need to know. Now look at this. This is here our GPT-03, our GPT-5, the Gemini 2.5 Flash, and the 2.5 Pro. They have different accuracy, 50, 73, 70, and 83, but complete different token length for the reasoning process to arrive at the same conclusion. Just look at here, for example, the Flash with 70% performance accuracy and the Pro. Plus 13 percentage point, much less token here in the reasoning process itself. Is this model more clever? So this is what we are talking today. We no longer treat tokens as free to multiply. Now the token length also becomes here an object for optimization. Let's have a look. If we do this with quite a lot of models, we have here the accuracy on the y-axis and here the token length here for the reasoning process here on the x-axis. Look, these are our best performers. GPT-4 Omni, Gemini 2.5 Flash and Pro. Then we have the group of GPT-5 and O3. And then we have here Q1 non-syncing, and then we have Q1 3 syncing, and you got it. But you see, the difference in the accuracy is then for a Q1 3 14B non-syncing to a Q1 3 8B syncing. Let's have a closer look. Those are now the numerical data for all of the tested LLMs. So what you have the number of tokens to arrive at the correct conclusion. You have the achieved accuracy, of course statistical. And then we have a new parameter. If we combine those two, this is simply the reasoning efficiency computed as the number of tokens per accuracy, or if you want, measuring the cost per unit of correctness. Interesting. So you see the top two performer in accuracy, here with GPT-5 and Gemini 2.5 Pro, are not the most reasoning efficient model. Well, GPT-4 Omni is the most reasoning efficient model, but only with an accuracy of 35%. So this is here a delicate balance. So you have to find the right balance for your task, what you want to achieve. You go for accuracy, or if it's really time critical and maybe too expensive, you also here take into account here the number of tokens. And if you go here, the next step, and we look at the 14B non-thinking and the 14B thinking, you see you jump from 33% accuracy to 40% accuracy, but suddenly the model uses here 3 times more token for the reasoning process. This takes more time. You get a little bit better result, but yeah, look at the efficiency data. So an equilibrium. So if this is the case, and this is the horrible world that we are facing here, what is the solution to make all those problems here go away and have all those models in a much higher reasoning efficiency class? What is the solution? Here is the solution for you. We have now a powerful new mechanism to build LLMs that are not just correct here, but also efficient and more reliable thinkers. How we do this? Well, what a coincidence. We have a beautiful application of classical statistical physics here to modern neural networks. Nice. Let's have a look at this. How we do our reasoning normally in a chain of thought sequence. No? And we have two basic chain of thoughts. You have an explicit chain of thought, generating here the discrete token. When you say, hey, let's think step by step, brittle, one wrong token can derail the entire reasoning path because it's an autoregressive system. And then we have implicit chain of thought, like soft chain of thought. Here we go not with the vocabulary items here, after the softmax, but we operate still in a continuous latent space, generating here our famous soft sort tokens, nothing else than vector embeddings, instead of the actual vocabulary elements. And we find out this is much more efficient, but it lacks consistency. And it's not a way to go with self-consistency. So you might ask, is there now another way? I'm so glad you asked, because now I can introduce to you a third way to do chain of thought here with the EBM methodology or the framework. We have now an interwoven energy-based AI model. Here we have the main paper of today. University of Oxford, Tsinghua University, Tencent, Southern University of Science and Technology of China, National University of Singapore, published November 10, 2025. Think consistently and reason efficiently. Energy-based calibration for implicit chain of thought sequences. Now, I already mentioned a little bit, it has something to do with physics, yes, and of course we go with a probability distribution that is a Boltzmann distribution. Now, this is easy. If you go with the energy thought, you say immediately, yes, of course, a Boltzmann distribution. Here's it, if you have forgotten how does it look. We have here our parameter I is a latent thought embedding, C is here our content, T is a temperature parameter, and E is a scalar energy function for any given state I will explain this in a little bit more in detail. If you're not familiar, I also use ChatGPT. Like here, I don't write it down. I just say, hey, explain the Boltzmann distribution. And the explanation by ChatGPT is, at a given temperature T, not all particles have the same energy in an ensemble. Instead, the probability that a particle has a certain energy E decreases exponentially with an increasing energy. And this distribution is a probability distribution, and this particular distribution is called Boltzmann distribution. Here we have here the Boltzmann constant here, temperature in Kelvin, and this is here the main idea hundreds of years ago from theoretical physics that we apply now in computer science. So you see, transdisciplinary. What we have now. Now you know a nonlinear integral differential equation is not so easy to solve, so we have to move to phase space and we have density function. And hey, don't forget Wikipedia. It's almost dying. It would be really a shame if Wikipedia is not continuing. It's such a beautiful instrument here. So if you look at Wikipedia, you see exactly how to solve here, exactly under quotation mark, to solve here this equation. But now in computer science, here neural networks, we have a hybrid multi-stage architecture. Let me explain this in detail. It is not simple. I need just a moment here of your attention. Attention, pun intended. We have two LLMs. We have a small, so let's go with a large assistant model, and we have a base model. Now, this assistant model here, make it smaller, takes here the input prompt, here the human prompt, and generates here a sequence of initial latent sort embeddings. Think of it as the LLM's first unrefined draft of a sort process. And then we have the main champion here, the base model, our GPT-5, or whatever you have. Here, you ought to go with a Llama 3.1 8B. And this model now receives here the final calibrated latent sort embeddings and uses them to generate here the explicit reasoning text and the final answer. And you might say, but hey, there's something missing now in the middle, eh? So we have one small LLM that generates here a sort process, and then we have a large LLM that takes in something here that has already a vector encoding, so we do have to have here a certain layer of transformation. And of course, this is the concept of soft chain of thought. And they say to exploit a continuous space reasoning with soft chain of thought, they use here the last layer hidden states from the small assistant LLM as the soft sort tokens rather than the discrete tokens obtained after vocabulary mapping. And they say staying here in the latent space avoids information loss that is simply inherent in an autoregressive decoding, of course. So with soft COT, we were aware as an alternative here to further fine-tuning. You have a smaller LLM, you look here at their last hidden layer states, you convert them here into a vector representation. You have then a projection layer to bring it up to the dimension of here the base model, and then you inject this here into the base model, and the bonus you get is you do not have catastrophic forgetting like you normally have with fine-tuning. Now the added component that we have now with our energy-based model is it introduces now on this latent space, in this latent space, a differentiable energy function E that is defined in the sort embedding space. It's a little bit abstract, but never mind. Just imagine that we have this space that is here the intermediate space between these two LLMs, and on this space we have now simple and mathematical optimization procedure. And this parameter that we are optimizing is here an energy function, whatever this is, never mind. So you see, we have the mathematical apparatus to say, okay, a space, we have an optimization theorem, and we optimize for a certain parameter, and those are the formulas. Let's go for it. Beautiful. Turns out it's not that easy because there are some little tiny details. But in general, this NFG function that we are going to define in a new AI model, so we will have one AI model, a second AI model, and a third AI model. This energy function explicitly calibrates here the latent sort tokens via kind of a gradient descent form, guiding them towards a lower energy region, does correspond to more task relevant, and guess what? Energy is connected now to logically consistent reasoning trajectory. So what we try to achieve is go away from an autoregressive next token prediction and have a little bit more of a past history logical sequence that we can integrate into the prediction process. And we try to do this here with a new calibration and normalization on the energy function. So let's be a little bit more operative. We need three additional elements between those two LLMs. The first, a projection layer. Simple, yeah? If we have here a smaller model, I don't know, a 512 layer model, and we have here a Llama 3.1, I don't know, but let's say it has 2048 dimension, then we have to have here a mapping from the output of the assistant model to the input of the base model. That's it. Input to the input, map to the input embedding space of the base model. Now, I told you this is going to be an AI model with weight tensors, and you guessed already why. Because if this is frozen and this is frozen, guess what model we're going to optimize in our training process. Talking about another model, by the way, yeah, almost forgot, the energy-based model. Of course, we have to have this model too. Now, this is, if you want, the core of this invention. The ABM, in the case of the authors, is a simple multi-layer perceptron, but it can be any AI that you like. But let's go with an MLP, takes those latent sort embeddings and evaluates the energy and predicts here a certain scalar energy point. What is this energy? Energy is, in my simple words, equivalent to a logical plausibility. And then, if we build this energy manifold in multiple dimensions, then we need an optimization process, as I told you, on this energy manifold, and therefore we go with a Langevin dynamics calibration. So what Langevin do is it refines the sort embedding further. It, if you want, chips away the bad parts of moving now the embedding downhill to the minimum of the energy landscape. This is what you are familiar with here, this whole of backpropagation and everything from AI learning. So you see, suddenly our architecture for this becomes quite dense. An assistant model, a base model, a projection layer as an AI model, an AI energy-based model, and a dynamic calibration methodology here that is based here on gradient descent here with a little bit of an epsilon noise vibration. This is Langevin, what it is in essence. Okay. And then, when we run through all of this, and remember the base model is frozen, so what we get back as backpropagate, what do we optimize? We optimize the weights of those two, of the projection layer and the energy-based model. And of course, you can integrate here the projection layer and the energy-based model and train them in tandem, but in general, let's make it step by step. So we run through all of this, we backpropagate everything, and then, like in normal AI training, we modify now the weights in our projection layer. Because the base model is frozen, we do not change the weights. We just have to change here the weights in the projection layer so that the base model, in the end of the causal reasoning process here, provides a better chain of thought that is more to the ground truth, closer to the ground truth. So you see, the training process can, before we establish the system, can be now quite intense. And then we have some open question with inference run, but we're still at the training process. Take a step back, think about it, what have you built? We have built an energy landscape in a high-dimensional mathematical space as defined by the trained EBM model. Of course, this is why we do it. And then if we have this energy landscape in multiple dimensions, we want to find the local minimum in there, because in there is a stable solution for molecular structure or reasoning traces. So the system uses now Langevin, the dynamics of Langevin, to refine them in an iterative process that nudges here the sort embeddings a little bit more downhill, to this minimum in the energy landscape. Think about a mountain, and somewhere down in the valley you have a beautiful lake. This is exactly where we want our sort embeddings to go, because this is a stable solution down there. And how we do this? Well, our old friend, we have a gradient descent. Now on the energy function. And if you ask yourself, hey, why Langevin? Well, the randomness is crucial in physics and statistics for ensuring you can properly sample from a probability distribution and avoid getting stuck in poor local minima. Therefore, you need this additional term that wriggles around a little bit, this epsilon term, so you can come free of local minima and explore and find your global minimum. Okay, great, this is it. So you only more or less train here a small energy-based model, the MLP, and train then a projection layer that maps you the assistant model outputs to the base model input space, the embedding space, the complexity of the embedding space. What could go wrong in this training process, you might say, no? Sounds like an easy thing. Well, of course, if we look here at this flow diagram, you see how we start. We have our assistant model, we have our base model, and then we were just talking about here the training process, not yet about the inference process. So the assistant model is frozen. Then you have this projection on a higher dimensional vector space of the base model. So we work exactly in the vector space of the base model. Then we have our training process, we have our training data, and then with Langevin, we have the separation here of the path that we are looking for and the path that we do not like. So we have contrastive learning paradigm here, and we bring it together. We define a loss function here, and on this loss function, this is exactly how we train here our EBM model and the projection layer together to have here a better solution for the base model. So whenever we compare now the output of the base model with the ground truth, we know how good we are, and when we back propagate everything back together, we change the weights back in the projection layer, and then we change the weight here in the ABM layer, and then we find here a better solution, and this is the classical learning process. So let's have a look how we do it now precisely. So we have to generate the training data for the ABM on the fly using here standard instruction tuning data sets, like classical mathematical data sets, and they have here a certain pair construct. You have a problem and a correct solution, and these are the pairs that are our training data. Problem, correct solution pair from a data set. So what we do now to train our EBM, we have now the positive sort. So let's generate the positive sorts. You feed a problem into the frozen assistant model. It produces a sequence of initial latent sort embeddings, whatever the complexity is. And since this sort process is paired with a known correct solution from the pair, we label the sequence of embeddings as our positive sample. Yeah? It is an example of a sort process that can lead to the correct, to the right answer, to the known correct solution. So we have the good answers. But for contrastive learning, we also need the bad answers. So let's generate the negative sorts for our EBM model. And if you want, this is the clever part, because we create these negative samples just by corrupting the positive a little bit. Yeah? And the authors here of the paper uses here the short-run Langevin dynamics exactly for this. So you take, if you want here, in a very simple explanation, the good sort embeddings and slightly perturb them, pushing them away from the low energy region that it currently occupies. And this could be done by randomly adding some noise or taking a small step up the energy gradient instead of downstairs. So this clearly creates now a not as good, if you want, sort embedding. This is now our bad sort. A slight off-course version of the good one. I mean, it couldn't be simpler, no? And for every training step, you dynamically generate now the good sort, bad sort pairs. And the only job for our EBM AI is learning how to distinguish them. Because you assign a low energy to the good sorts because you want to have here the perfect local and global minimum, and the high energy, high scalar to the bad sorts because you want to move away from those places. So you create the learning signal from the existing problem-solution pairs, for, let's say, if you work in the mathematical knowledge domain for mathematics. Therefore, short summary, EBM calibrates the latent sorts in an embedding space through contrastive energy learning. EBM assigns the low energy to the coherent reasoning tokens and the higher energy to the implausible reasoning tokens. Now, let's change a little bit the perspective. Let's change the framing. If we want to code this, we have at first to build a mathematical framework for this. Because only if we have a mathematical, theoretical physics framework, we can then encode this into C++ or Python. So, for a very short moment in time, we have a little bit of physics. So we have now the loss function design, and you have here a screenshot here from the original paper here. Why I want to show you here how they define the loss function. It is simply the sum of the LLM loss function and our EBM loss function here with the projection. And you have simply a ReLU, and there's nothing that's strange that you are not familiar with. You have the high and the low, just as I told you, the low energy latent and the high energy latent, so the positive sample from the target data distribution and the negative sample. And this is exactly what I just told you looks in a little bit of a theoretical physics formulation. Now, if we go and have a look at closer here at the loss function for the LM and the gradient flow that we need for our mathematical optimization methodology, we analyze here the gradient propagation of the language modeling loss through the Langevin sampling step, and then you have a little bit of mathematics, and then you arrive here at the gradient formulation. Great. But this is just the gradient for the first term. You know that we are looking here for the gradient for the second term. And the second term was for the ABM model. And after some sorts, or you can read here all the details in the paper, please have a look at the original paper. You find now here the gradient here also, the analysis here for this loss function here also in this beautiful formula. And if you have a little bit of a closer interpretation of the gradient propagation through the Langevin steps, here is it and why we arrive here at this particular result. And now we just add it together. You see exactly here our formula. Loss function is just an addition here of the LLM loss function of the ABM loss function. We just, in the simplest case, added them together and the nabla of them is here. So therefore, this is now our gradient formulation. And this gives us now an idea. If you want to code this, C++, Python, whatever you like, this is now what you code. Or you ask your code LLM, your code assist, or whatever you have, hey, code this now in my preferred language. Okay, let's come back here to the main understanding part. Let's change the framing, the perspective again. So what does the gradient from the EBM loss do? In principle, it teaches you the ABM model and the projection layer. I told you we can combine them. How to create and transform the sorts such that the positive examples land in the low energy region and the negative examples land in the high energy regions. Because we want to have a descent, gradient descent here to the local and global minima. The gradient from the large language model loss is backpropagated through the Langevin steps and the projection layer to refine the projection, of course, because the weights of the base model are frozen. So this now teaches, quotation mark, the projection layer weight tensors to reconfigure in a way to transform now the assistance output into the sort embeddings in a way that not only look good to the EBM, but also in the next step, when it is inputted into the base model, the base model can generate the correct final text that is now real close to the ground truth of our training data set. So you see, the training process is now split into multiple layers and into multiple loss function where it is not that simple, but they found a nice, elegant mathematical solution to this. And therefore, as I told you, EBM and Langevin dynamics are codependent. If in the next step of simplification, the EBM provides the knowledge of what constitutes a good reasoning step in our chain of sort construction, and the Langevin dynamics provides the action of moving towards that good reasoning step. Because this is the main difference, maybe I have to repeat this again, you don't go with a self-consistency that you say, I generate 10 reasoning traces, or I let my LLM generate 100 reasoning traces, and then I just compare those, or I have a self-consistency algorithm, and I select now this single reasoning trace out of this 100 that is the most dominant in this set of data. We want to be efficient, we want to be fast, we are time critical. So now with this EBM and Langevin dynamics, we say we don't do this. We generate here autoregressive LLM next token prediction, but for this next token prediction, we have here in front of the LLM now the projection layer, an assistant model, we have an EBM model, and we have here a dynamic gradient descent calculation to further refine that the next token is absolutely the right next token given the training of the EBM model. So it all depends if you have excellent, very beautiful data quality to train the EBM model, your output here of the base model will be outstanding, better than anything else. But if you have not the best quality of your training data for the ABM or for the projection layer, yeah, you are into some troubles. Framing. Another try. The energy landscape that I told you is a high-dimensional space, a subspace here that evaluates here, if you want, the goodness, the appropriation for a beautiful causal reasoning trace of a single sort token at a single step in time. You remember? We are still at an LLM, we still have autoregressive next token prediction. We just want to improve here this next token prediction at every single step in time. So the model traverses this landscape that is now additional built as a forerunner to the main LLM. Step by step, I build one complete reasoning trace in this iteration. Let me give you another example. I'm here in a mountain, what a coincidence. I like physics, what a coincidence. So let's do this. So let's say you, the assistant model, at any given location I am here, your current sort context, you propose a single next step. If I step out here in the mountain here, the next latent step is the next latent sort token in AI. Now let's say I have here in my mountains a GPS system. This is of course our EBM that we have now as an additional guide. And this EBM instantly evaluates the difficulty with the energy parameter of taking that specific step from my current or your current location. So if I'm standing here in my mountain landscape or you are standing in the energy landscape of AI, this EBM sees now the landscape, all the epsilon environment of all possible next step in your environment from where you are standing right now. And then we have with GPS a better calibration. This is what I showed you with large model dynamics. Before you commit to your proposed step, before you do it, the GPS corrects now your plan. It says, I have further analyzed here the situation, I have further analyzed here the energy landscape, and your proposed step is a little bit uphill. So if you adjust it slightly, let's say to the right, this way, we have down the gradient, you will land on a much safer, lower ground where you have a stable solution. So it refines your single proposed step. If I'm standing in my mountain terrain, or if you are the AI, it refines your single next proposed token prediction. And then we both take the step, I in my mountain, you in the AI, refine, calibrate the step, and now you are at a new location, I also, and now it all starts over again. Your context now includes the calibrated sort of before. And now we repeat this, and you see, we have now a new GPS calibration step that, if you want, improved our next token prediction, my next step in the Alpine region here to land here a next safe step. And this is what is happening here. So you see, we take the mathematical formula from Boltzmann equation here, from heat transfer and everything, from physics, we applied it to computer science, but the ideas are simple. You see, I can present it to you here like in the form that we are standing somewhere in the mountain. And now the question is, if you want to reach your goal, your target, your hut that you want to sleep over tonight, what is your next step? What is your path forward? What is your next token prediction? And this is exactly why the EBM chain of sort framework is so efficient. It is not generating 100 chain of sort traces and then evaluating what was the best trace. It is building one EBM chain of sort trace, but with most care and with here GPS prediction. Okay, what are the results? They did not have the idea, they built this system, they implemented this system, and they checked and benchmarked this system. So here we have the results. If we look now for the accuracy that we can achieve with different methodologies, you see here in orange we have zero-shot chain of thought, zero-shot assistant, or LoRa fine-tuning in red. Then we have coconut. Here we have soft chain of thought. And here finally the method of today. And if you see here the accuracy for a mathematical benchmark, you see this result. And if you go here for a consistency rate, you see this result. If you really want to have a deep dive, I would recommend, I had to do this because I was not able to understand this paper only by itself. I had to go back and read the paper of the soft chain of thought. You see, this one here, the one before, because it builds on this model and it just further integrated new components. But the main reason why soft chain of thought was built and the primary mathematical explanation and the primary thoughts of this were not presented in today's paper, but they were hiding, of course, in the paper from May 27, 2025, where they built this and explained this soft chain of thought. So you see, one builds on the other, and you always have to read at least the direct study before your current study. Otherwise, I could not decode here the current paper and the current understanding. If we look now here at the performance data, you see here compared to a zero-shot chain of thought, LoRa fine-tuning, coconut, soft chain of thought, and of course ours as the new method that we had in this paper, you see here on different benchmark, on average here, the last column, okay, compared to soft chain of thought, which was much simpler, much simpler, which had a 70.5% performance. Now we are 72.5% performance. So personally, I'm a little bit in doubt that these 2 percentage points are really necessary, because just think about what we had to build. We had to build the assistant model, we had the base model, we had the projection layer, we had to train the projection layer, we had the ABM model that was integrated into the projection layer, but we also had to train them, we had to build them. Then we had to apply not a simple gradient descent, but this gradient descent with a little bit of an epsilon wiggle. Then we had the whole training process in itself. We had to generate the training data. And then we had the inference one where we had further optimization. So there's a lot of things going on for just 2 percentage point improvement. So is this an operational model that I would recommend to you? No. This is a beautiful experiment. It shows us the direction for the next generation of AI models. What can we improve? How should we improve the training process? This is something here, an internal training optimization for further AI models. But unfortunately, I would say all the complexity that the authors built into this new model, if you see here some benchmark here like common sense, you are more or less stuck here with the same result like soft chain of thought, who did nothing on the energy optimization. So maybe you are the one who has here the next idea, a brilliant new thought how we can further optimize this model. And maybe you published in 2, 3, 4, 5 months your first paper where you say, hey, I had a brilliant idea. To build on this, I'm now standing on the shoulders of the researchers before me, and I can further improve AI models. And this would be great. This is the goal of my YouTube video. So I hope you enjoyed it. You had a little bit fun analyzing here 2 brand new AI research papers. Maybe you subscribe. Maybe you want to become a member. You join my channel. Anyway, I hope to see you soon in my next video.